Hello, everyone, and welcome to this video presentation of our paper on the hardness of edit distance to a fixed sequence and some other results of this nature. This is joint work with Virginia. Let's start by defining the problem. So first, in the standard definition of edit distance, we're given two sequences, X and Y, and the goal is to compute their distance. That is the minimum number of insertions, deletions, or substitutions that is required to transform one of the sequences into the other. This problem has an n-squared upper bound with dynamic programming and conditional n-squared lower bounds under the strong exponential time hypothesis, SETH. So we can think of the complexity of this problem as quadratic. But now, suppose that one of the two sequences is fixed in advance and never changes. So in this edit distance to X problem, only the sequence Y is given as input, while X is fixed. So the input is one sequence rather than two, and the goal is to know the distance between the given input sequence Y and the fixed sequence X. So what is the complexity of this problem? Of course, that depends on X. And actually, to be more formal, we need to talk about a family of sequences X that contains one sequence X sub n for each length n, but that's just technicality, don't worry about it. Okay, so what is the complexity of this problem? So here are some examples. When X is the all zero sequence, then the problem is essentially asking for how many zeros does the given sequence Y, how many zeros appear in it. And this can be easily checked and solved in linear time. Maybe a bit more interesting is the second example, where X is the sequence 0, 1 to the n over 2. I'll leave it as an exercise to figure out the complexity of this problem. But this generic problem could be interesting if there's one sequence X that we are interested to ask a lot of distance queries against. So for example, if there's some reference genome, say of some COVID virus, that we will be testing a lot of other genomes against. So we would be interested to know if this distance to COVID problem can be solved much faster than the worst case edit distance. And in general, someone or some company might have a certain sequence X, and they might only care about computing the distance to their X. And they would like to know, is the complexity for their problem quadratic, or perhaps it's possible to solve it in linear time for their data. So the first question that comes to mind in this context, from a theory perspective, is whether quadratic time is ever required for any family X. After all, knowing X in advance is a big advantage because we can design an algorithm that is specific to X. So does this edit distance to X problem ever have complexity n squared? Or maybe for any family of sequences X, there is some algorithm that can compute the distance to X in linear or some subquadratic time. This is the question that we answer in this paper. And our results will follow from a more fundamental result on the orthogonal vectors problem, OV, that we will present next. Most lower bounds under SETH for problems in P are proved by a chain of reductions that starts from KSAT and then goes through the OV problem. This is a simple problem with quadratic complexity that can be reduced to many problems in P, like the edit distance. The input is two sets of n vectors, A and B. Each vector has dimension d, which can be thought of as log n, and they are binary. The goal is to decide if there is an orthogonal pair, which simply means a pair of vectors such that in each coordinate, one of them is 0. In this example, the highlighted pair is orthogonal. It's easy to solve this problem in n squared times d time by checking all the pairs, and a reduction from KSAT shows that this is essentially the best possible, assuming SETH. Backwards and Indic reduce OV to edit distance to prove their n squared lower bound. And there are many hardness results that are proved in this way. Here, I'm only listing a few of them that will serve to highlight our results. The subtree isomorphism problem, the closest pair problem, and regular expression matching. So here's the main result of this paper. We give a new reduction from KSAT to OV in which one of the sets is fixed and doesn't need to be a part of the input. So just like we defined edit distance to a fixed sequence, we can also define OV with a fixed set A. This is the OVA problem. And our new theorem says that there is an explicit family of sets A sub n, such that OVA is n to n squared hard under SETH. So it's essentially the same strong hardness result that we had under SETH, but now for a more restricted version of OV, where only one set can change. The only weakness of the new theorem compared to the previous one is that the dimension of the vectors needs to be polylog n rather than O of log n, but this is not a problem for most applications. For example, by plugging our new hardness instances of OV into the reduction of Backrus and Endick, we get the hardness we were asking for edit distance as a corollary. So there is a fixed sequence X that we get from the hard set of vectors A, such that the edit distance to X is n squared hard. So we can now show a family of sequences X such that edit distance to X is not easy at all. You need the same worst case, the same n squared time that you needed for the worst case problem where X was part of the input. And as you will see, this hard sequence X can be described explicitly and efficiently. So this answers the first question that came to our mind in this context, and it leads us to wonder if some stronger and deeper understanding is possible. So can we provide tight bounds for edit distance to X for any X? So do we have the tools to be able to quantify how much time it should take to solve the problem for whatever sequence X we are interested in? It would be really cool if such a classification was possible that would determine the complexity based on some properties of X. Unfortunately, I have no idea how to do that. So besides edit distance, we can prove lower bounds of a new kind for many other problems using the previously known reductions from OV. For example, the subtree isomorphism problem asks if one tree is contained in another. And now we can get the same hardness even if the subtree we search for is always the same. Another example is the bichromatic closest pair problem. And now the lower bound holds when one set of points is known in advance. Yet another example is the regular expression matching problem. Now we know that there's a fixed regular expression such that deciding if a given input string matches this fixed expression is SETH hard. And essentially, any reduction from OV now implies a stronger hardness result. For some problems like edit distance and the ones I'm listing here, it's possible to explain what is this stronger result. But for others, like for computing the diameter of a graph, the consequence is less natural. So we can now say that the diameter is hard to compute even when half of the graph that we're interested in, half of the graph is fixed. But it's not so clear why that is interesting as a problem. So, yeah, there are more interesting results that you can derive in this way. For example, for LCS, the longest common subsequence, the Frechet distance, and so on, we do get some new natural versions with a fixed set that are now hard. So before discussing more implications and results, let's talk about the proof. I'm sure many of you have already seen the reduction by Williams from SAT to OV. It appears in many talks on fine-grained complexity. And the new result will follow by modifying this reduction. And both the old reduction and the new one are pretty simple. And I can explain each of them in 1 or 2 slides. So let's do that. And let's start with the old proof, which was from iCalc 2004. The goal is to show that a subquadratic algorithm for OV implies a faster than 2 to the n algorithm for KSAT. And this faster than 2 to the n running time is enough to refute the strong exponential time hypothesis. Which I didn't state this hypothesis explicitly in this talk, but for all the purposes of this talk, you know, this running time would refute it, so don't worry about it. And so here's the outline of the proof. Suppose we were given a KCNF formula phi on n variables and m clauses. Here's what the formula phi might look like. The reduction constructs two sets of vectors, A and B, each containing 2 to the n over 2 vectors, and their dimension is m. The dimension is the number of clauses in the input formula. And they have the property that there exists a pair of orthogonal vectors if and only if phi is satisfiable. This is enough to prove the theorem because subquadratic in 2 to the n over 2 is sub 2 to the n. And moreover, the dimension m is logarithmic in the number of vectors. This is because by the sparsification lemma, it's enough to solve ksat when m is O of n. So that was just the outline of the reduction. Now let's dig into the details. Let's say that the variables of the input formula phi are x1 up to xn, and let's say that the clauses are c1 up to cn. We define the vectors as follows. The dimension is m, and each coordinate corresponds to one of the clauses in phi. And for each partial assignment alpha to the first half of the variables, we define a vector v sub alpha as follows. In coordinate I, we put as 0 if the partial assignment alpha satisfies the clause ci, and we put a 1 otherwise. So a partial assignment sets some of the variables to true, some to false, and some are left undetermined. In the case of these alphas, they leave the n over 2. So they give a true or false assignment to the first n over 2 variables and leave the other n over 2 variables undetermined. And we say that a partial assignment satisfies a clause if one of the literals of the clause is already true by the assignment of the partial assignment. Otherwise, we say that it doesn't satisfy it, or meaning that it might leave it undetermined. And now for each beta, that is a partial assignment to the second half of the variables, we have a vector v sub beta that is defined in a similar way. All the v sub alphas make up the set A, and all the v sub betas make the set V. They both have size 2 to the n over 2 because there are 2 to the n over 2 partial assignments to a set of n over 2 variables. The key claim that can be verified easily is that a pair of vectors is orthogonal if and only if the corresponding pair of partial assignments make up a full assignment that satisfies the formula. This is because for the pair to be orthogonal, it must be the case that every clause is satisfied by at least one of them. Or else, if there's some clause that none of them satisfy, then the corresponding coordinate will have a 1 in both vectors and they would not be orthogonal. And so the point is that there exists an orthogonal pair in the sets A and B if and only if there exists a satisfying assignment to the formula phi. And that's the end of the proof. Now, jumping from iCalc 2004 to iCalc 2021, let's see how the proof, the new proof is different. The goal now is to have a reduction where the set A is fixed. It only depends on n, but not on the input formula phi. And here's the new outline. It's very similar to the one before with the change marked in green. The dimension of the vectors is now roughly n to the k and not n. So which ends up being polylog in the number of vectors instead of log as before. But everything else is the same. We're still going to define two sets of vectors and show that there's an orthogonal pair if and only if the formula is satisfiable. And of course, the main difference will be that the set A won't depend on phi. And here's the full reduction. Again, let's say that the variables are x1 up to xn, and the clauses, the given formula phi, are c1 up to cn. This time, we will also look at the set of all possible k, c, and f clauses over n variables, and ordered in some arbitrary way, let's say lexicographic, and let's call them c tilde 1 up to c tilde n to the k, 2 to the k times n to the k. For each one of the c tildes, there will be a coordinate in the vectors. As before, for each partial assignment alpha to the first half of the variables, there's a vector, and there's a vector for each partial assignment beta to the second half of the variables. However, Now the alpha and beta vectors are defined pretty differently from each other. The V sub alphas are similar to before, with one crucial difference. We look at all possible KCNF clauses rather than only at the clauses that are in phi. That is, there is a coordinate for each C tilde I, not just for the CIs. But other than that, the definition is similar. We check if alpha satisfies the clause C tilde I, and then put a 0 or 1 accordingly. All the V sub alphas go into the set A, and notice that this set doesn't depend on anything but n and the constant k. In particular, it doesn't depend on phi. So this set A is just fixed set. And now here comes the trick. When we define the V sub betas for the set B, we do look at the given formula. And if there's a coordinate that corresponds to a clause C tilde I that is not actually in the input formula phi, we hard set the bit to be 0 in all the vectors in B, which essentially removes this coordinate from consideration. Because it doesn't matter what the vectors in A have in this bit. If all the vectors in B have a 0 for that coordinate, then this coordinate will not affect the orthogonality of any pair. So the ith coordinate is set to 0 if either of the two conditions happen, either beta actually satisfies the clause, or if this clause, C tilde I, is not actually in the input formula phi, in which case we also put a 0. And the same key claim from before still follows in pretty much the same way. But the point now is that the clauses that are in phi, the same argument goes through in exactly the same way. But for the coordinates that correspond to clauses that are not actually in phi, well, they don't affect anything at all because they are always 0 in the set B. So the same proof goes through. And that's it. That's the new reduction. Let's take a moment to reflect on what is this hard set of vectors, this fixed set A that makes OV hard. Each vector corresponds to a partial assignment, and the vector encodes which of the possible KCNF clauses are satisfied by this assignment. So you can see that it's a pretty structured set of vectors. Perhaps it might remind you of some error correcting code construction. And it has the following properties, among others. These are just simple things that you can notice. Each coordinate is 1 in a 1/2 to the k fraction, roughly, of the vectors, because there's only one out of the 2 to the k choices for the k variables in a clause that are not satisfied. And if we look at two different partial assignments, the two corresponding vectors, they will differ in at least n to the k minus 1 coordinates. So anyway, the point is that the set is pretty explicit. And if we want to see the hard sequence for edit distance, we have to follow the reduction from OV. And what you get is a sequence that looks like this. There's some simple vector gadget encoding each vector. And all of these gadgets are concatenated with some appropriately chosen and cleverly chosen separating symbols that are placed between them. One interesting point is that the sequence in the hardness result can be made not only fixed, but it can also be made to have a binary alphabet by the reduction of Brinkman and Koima from OV. Now, finally, let's talk about some other results in the paper. The lower bound can be generalized from OV to KOV in a straightforward way. Where in this problem, we have k sets of vectors, and the goal is to find k that are disjoint. So the n to the k lower bound now holds even when k minus 1 of the k sets are fixed. This directly implies an n to the k lower bound for the k longest common subsequence problem, k LCS, when only one of the k sequences is given as input and the others are fixed. Another result that can be boosted to the fixed sequence setting now with a similar trick but a different proof is the connection between shaving log factors and circuit lower bounds. So shaving a super polylog factor for edit distance, even when one of the sequences is fixed, has breakthrough consequences in complexity theory. And finally, there are consequences for algorithmic models where one is allowed to pre-process part of the input in advance. For edit distance and such problems, it was already known under SETH that the quadratic lower bound cannot be broken even if we pre-process one of the sequences in arbitrary polynomial time. Now we can rule out an even stronger pre-processing that uses polynomial space, but this is under a non-uniform version of SETH. I want to end with the open-ended question that I've mentioned before. Is there a way to classify the complexity of edit distance to X for any family X? So based on the internal properties of the sequence X, be able to tell me how hard this is going to be to compute the distance when the other sequence is worst case, but the sequence X is fixed. How hard is it going to be to compute this distance? Thank you for your attention. I hope this was an interesting talk.